start with a little introduction. So welcome everyone. Welcome to this this meetup, which is organized by Codurance and also by the Software Crafters meetup organization. In this session we'll have Mash, who is going to give us a little introduction to Clojure. First of all, a couple of mentions here. Well, Codurance is it's lending us the space to run this this session. Codurance is a high-end IT company, consultant IT company, which was founded in 2013 by Mash and Sandro, who you may know. And since then, they've Codurance have pushed the London software craftsmanship community. Why we do that? Because we mostly want to give back to the community. We want to improve our profession. We want to improve we want to share with all of you we want to share our work. We want to share how to do things in a better way, and that's our philosophy, which is completely aligned with Mash's philosophy. That, well, he firmly believes that a well-rounded software craftsman must have a keen interest in all aspects of software creation, including process, people, technology, user experience, development, operation, maintenance, and social impact. So welcome you all. Thanks for joining us in this session. Elena, I don't know if you want to say or add something before moving to Mash?
It's okay for me.
All right, so Mash, the stage is all yours.
Oh, thank you, Javier. I wrote that bio a while back, but I still believe those. I forgot I wrote it as well. But welcome everybody. Thank you for joining us. So this is an introduction to Clojure. So the idea is to give you a little taste of Clojure, why I think it's such a beautiful language, but also the basics of what kind of the basic features of Clojure, right? So I will take quite a fast tour through the language, kind of demonstrating a few aspects that I like about it. I'm happy for this session to be interactive, so please stop me whenever you want. If you have a question, just go ahead and ask the question. I won't be able to keep an eye on the chat, but I've asked Helena and Javier to keep an eye on that. And if there is a question there, they will raise a hand and ask me to kind of stop, and then you can ask the question, or they can ask on your behalf. So that's fine. If you find that there is I'm going too fast, or you can't see some of the code, just let me know, so I'll zoom in, right? But and also if you find that I'm going through too basic kind of features, just bear in mind that other people may not have seen the language, so it might be good for them anyway. So as I go along through the session, things will become a little more complicated, a little more advanced, but stop me at any time and I'm happy to explain further. Okay, so without further ado, let's get going. So I'm gonna share my screen. Can you see this? So it's a IDE, yeah?
Yep.
Yep, we can.
Yeah, perfect. All right. Okay. So the first thing is Clojure is a dynamic language, and it has a REPL. So for those who don't know what that is REPL, pronounced REPL, and it stands for Read, Evaluate, Print, Loop. And all that means is it's a fancy way of saying that you have a interactive shell, and you can type Clojure commands in there. So this makes there's quite a few languages with a REPL. It makes experimenting quite easy, and because it's interpreted, it's quite fast. But some compiled languages tend to have REPLs these days as well. So for example, here is my first 1 + 1, and it will show me what I typed, and it also gives me the result. So the result appears up here. Yeah, so that's effectively the REPL. There are a few things in the REPL that are built in for you to make things easier. One is that you can kind of, just like a normal command shell, you can go back in history and execute something. You can also get documentation on something. So for example, print ln is a function, and I can say, give me the documentation. It tells me it's the core documentation for print ln that will print out for me. I can also do a find doc with a string. So that actually goes through all the APIs of Clojure, and you will find anything that is called print ln, right? So for example, there's print ln str, there's print ln, there's print, and so on. So you can kind of navigate through the Clojure documentation in that way as well, right? So that's effectively the REPL. So next let's move into the language itself. So Clojure is known as a homo-iconic language. It's what makes a language extremely powerful. So what does that mean? It basically means that in Clojure program is written as a data structure, right? So that's why it's a dialect of Lisp, which stands for Lisp Processing Languages. And what that means is that what you are writing is a data structure, and that's a program. So for example, this is how you write a list in Clojure. So this is a list of 2 elements, 1 and 2, and let's say 3, right? So if I enter this, you get an error, because actually this is the only other special thing that Clojure REPL or interpreter does, is it takes a list, and lists have special meaning in Clojure. It thinks that it's a program, right? So what it will do is it will take the first element of the program, which is of this list, sorry, that is 1, and it thinks that is the name of a function, and everything else in that list is the argument, or are the arguments, right? So it's trying to execute 1, thinking that you've given 1 as a function. So that's why I say that 1 cannot be cast into a, sorry, I'm trying to get rid of this. 1 cannot be cast into a Clojure language function. That's what it's telling me, right?
Mash,
but yes?
sorry, Mash. Yeah, we have a couple of questions here in the chat. Well, Albert, well, he asks if we're supposed to have Cider installed, or how's I guess he wants to follow you by executing himself the instructions.
Okay, so I would say that if you want to follow me, you can. You'll need a dev environment, either Vim Fireplace, and then connect it to a REPL, or if you use Emacs, then yes, you will need Cider installed, connected to a REPL. Or here I'm using Cursive plugin, which is the Clojure plugin for IntelliJ IDEA, right? Unfortunately, if you haven't got it installed and you wanna kind of walk along, this could be a bit difficult for you right now, because it does take a bit of time to install the environment. So what I suggest is that you go ahead and watch. There will be a recording of this as well, so we can provide you with a recording, and then you can follow that. Yeah.
Yep. We'll have the recording probably within the next week in our YouTube channel.
Yeah. Okay. Anything else? No?
Nothing
All
else.
right. Okay, so I'll continue. Right. There is someone's drawing on the screen. I don't know if that's something you can disable or not.
Let me see. This is the first time I see that.
Okay, no problem. All right. So basically, so once you have, as I was saying, it's trying to kind of call that function, but you can make it a list literal quite easily. So you can say this is the escape. So if I can say 1, 2, 3 like this, this is now, it's saying, okay, now I have a list, right? So that's quite cool. I can actually say this as well. I can say plus 1 and 2, and I'm saying this is a list, right? So I can now define, which is a variable, effectively. It's a var, but not really a var as you would know it. It is, they're usually, if you replace, you can't modify a var in place. You can redefine it, but again, it's redefined in a particular scope. So I would consider them to be more constants rather than variables, right? So if I say def, I'll say, x, right, is a list of plus 1, 2, right? So I can now say, well, what is x? And it says, yeah, it's a list of plus 1 and 2, right? But actually, plus is a valid function name, right? So if I say doc plus, it says it's a function, right? So I can now evaluate my list, which was x, and it will give me 3. So what it's done is taken plus and used that as a function and applied it to the other 2 arguments and returned 3, right? So 2 plus 1 is 3. So, this actually, so that's what I mean by homoiconicity, is that you have a data structure, which is a list, and Clojure is effectively a list, a program that is expressed as a list, right? And you can evaluate that. Now, this makes the language extremely powerful, as you can imagine, because you can on the fly generate programs, right? So that's what makes Clojure actually a very good language for, let's say, for creating DSLs and those kind of things as well, right? So next thing I would, as we were talking about this kind of this homoiconicity, I can also show you how a macro works. So macro is a built-in way for Clojure, in Clojure, for you to be able to generate code effectively, right? So one thing you notice is that, like, I have this prefix notation, which is actually standard in Clojure. So I don't say 1 plus 2, which you may be used to. In Clojure, the idiomatic thing is that function comes first, and 1 is also a function. It's we can think of it as an operator, but it's a function, right? So in Clojure, generally, you always have this function starting first and then the arguments, right? So you never really have infix operators. You don't have 1 plus 2, right? But let's say I really wanted 1 plus 2, right? So I can say, well, you know what? I can define a macro, and I can say this will take in my expression x, right? So let's just call it x. And now what I want to do is, this expression is infix, and I want you to change it into normal expression and execute it, right? So I can actually say, well, if this is going to be a list of plus 1 and 2, I can say, well, the 1 is, so take the first, the second element. So create a list first and take the second element of my x, may put that in first, then the first element, so of x, and then the last element of x. Yeah. So now, oops. macro. X list. Okay, so let's, in this case, oh yeah, sorry, my bad. So I need to call it something, right? So I can call it infix, right? So now I have a macro called infix, and I can now say, well, actually infix my function and take 1 plus 2, yeah? And it returns 3. So as you can see, I've created a DSL already. And what a macro does is actually allow you to take whatever. So in this case, it takes the list as a literal, and then I can rearrange it inside my code and execute it, right? Okay, so that's effectively what a macro does. And you can actually see using expand macro and so on, but I won't go into too many details because we have quite a lot to cover here. So are there any questions at this point before I move on?
Yes. Does this need to be a macro or could be just a normal function?
To do an infix operator, you could do a normal function as well. The only thing is though, then you have to pass in a literal yourself, and then you have to deref it. So if you don't want it to be a macro, it will be, you could do the similar thing, but in a much more complicated way. Yeah.
Okay.
So macro is already expecting whatever you're passing. So for example, you passed in 1 plus 2 as a list, yeah? If it wasn't a macro, what it would do is it will try to invoke 1 as a function. Before it passes the result into the infix. Yeah. So then you are kind of giving the burden to the caller to quote that, and then you're expecting it in quoted form, so things get a bit complicated.
One question: you regularly use macros? Because I always heard that you shouldn't use it much, but
yes. So you shouldn't use it much in your normal code base, for sure, right? But if you are writing some kind of plumbing or a library or a frameworks are usually discouraged in Clojure, but any kind of plumbing or things that sit around your application, you may have to write macros. It's good to know how to write them, so the tool is there. You should avoid it if you can, because of course it's code writing code, right? And if the macros get too complicated, it can get a bit difficult to read, but they are a very powerful aspect of the language. So you should know. In my kind of time writing Clojure past maybe 6-7 years, I've maybe written a macro in anger, maybe about 5-6 times, maybe. Not more, right? So yes, but I have not been writing many libraries and kind of plumbing. You know, a lot of those libraries are thankfully available for you to use it. Clojure has a very rich community, so when you're writing a proper app in Clojure, you tend not to have to write macros. Yeah.
I have a question. If you need to debug a macro, how do you do?
Oh, so you can do a macro expand, right? So for example, I had this infix, so I could do macro expand, and I can provide the form for that, right? So I think you have to, so basically what I've done is I've said, expand this macro. So this particular expression that I've used, expand it to see what is it exactly, right? So it tells me, without executing the code, it tells me the code that it generated, yeah?
Okay, thanks.
Yeah. So Javier, I can still see this yellow line on my screen.
We're, yeah,
getting rid of this.
Why don't you try to stop sharing screen and share again? I think maybe,
Okay.
do you happen to have a blackboard, a digital blackboard or something like that? Maybe
No, I
no.
don't.
Okay, a Wacom or something. No, I don't know
No.
what it is. So try
All
to stop sharing and restart.
Okay.
The
All right, I'll do that quickly. Yeah. Okay, and then share screen again. All right. Okay. So thank you for that. Right. So the next part is the Java intro. Right. So Clojure sits on top of the JVM, and one of the it is one of its strengths. Some would say weakness as well, because JVM is a bit cumbersome, especially at startup times. But it gives you a access to a very rich ecosystem, right? So, and it's very easy to actually use Java classes and methods. So for example, if I was using system out, I could do system out hello. Yeah. Oops. Oh yeah. So my bad. So I would say it's println. So that's the method, and I call it on the system out object, and I pass hello, right? So here's, you can see what it's done is, so effectively it follows the same convention. This is a Java method, println system. So out is an object that is a static field on the system class, yeah, and a rest is arguments, right? So function comes first, then the object that you are calling that function on, and then the arguments, right? So in this case, you said hello. It always returns nil. So in Clojure, every function must return something. So Java void functions would return a nil, right? So this is the side effect, hello, printed on the console. The return of this function in Clojure world is nil, yeah? In fact, you can also, do the same thing to, you can do the same thing with exceptions as well. So Clojure is quite pragmatic. On one end, it's very functional. It really discourages you from creating side effects. It discourages you from mutating state. So you can't do that by default. But on the other hand, it's fairly pragmatic in the sense that it knows it sits on a Java ecosystem. It will allow you to, for example, throw exceptions, which is the very definition of a side effect. But so, for example, you can.
Mash, sorry, can you share again? I was just setting one security toggle to avoid this yellow lines.
Okay, host has disabled the 10D screen sharing, it says, when I try to share.
All right, so that is my allow participant. Yeah, okay, go
All
again.
right.
Go again.
Okay,
yeah.
Let me try. Okay, you can see?
Yep.
Okay, cool. So for example, you can throw an exception. So I can actually, by the way, in order to create a new Java object, you just go like this. So you use the dot notation. So this is effectively like saying new exception, hello, right? If I return that, see, it's basically printed the stack trace for that exception, right? And I can cache that as well. I can say try, and then I can say exception, hello, and then I can say catch, exception, and I can call print ln or print, I think it's get message actually, dot get message. Yeah. So
is it possible to use the print stack trace from the exception?
Yes, you can. You can, yes. So yeah, so it returns the message on. So this is so is it? Yeah, of course you can do that as well. I'm just trying to remember the Dog. Catch class name, and expression. Yeah, so that's what I was trying to do. So yeah, you can actually do a dot print stack trace as well. I think it's catch exception.
Do you need to call it? Oh no. Do you need to call it catch clause or just catch is enough?
So no, it's just catch, right? So try expression, catch clause, and there's a finally clause as well. So this is just the catch, and then you kind of pass the class name, which is exception, and the name of the thing that you wanna catch, and then you can call the method on it, and pass the, I think it was get message. It's still passing that through. So okay, I'm not sure what's wrong here, but I'm probably missing something there, but it's effectively like that, right? But you can catch the exception within that clause, but it doesn't seem to be working for me. But I'll come back to that later on once we go through other things as well. But yeah, so effectively you can catch exceptions within Clojure code as well, Java exceptions within Clojure code, because you may need to do that when you're using the Java libraries, and that can throw exceptions, and you may need to handle them, right? So before we move on, any questions around that other than the fact that I couldn't get it to run? I could probably, what I'll do is, I think it's try exception. Okay, I'll show that later on if I may. Yeah. So any questions before we move on to data structures in Clojure? No? All right.
Okay.
So let's move into data structures. So Clojure is a list processing language, and the data structures are the main strength of Clojure. So they are all native in most languages, in fact, especially the C-style languages. You'll see that data structures are actually a library, right? In Clojure, they are part of the language, and this makes Clojure extremely powerful. So I showed you the list already, and I used a few things, so we can start that again. So I said def x is a list, and this is a way of escaping a list, as I showed you. So 1, 2, 3, right? So now if I do x, you get 1, 2, 3. That's a list. You can do many things on it, right? So you can say first of x is 1, last of x is 3, right? You can say nth of x at 1 is 2, right? So it's a 0 indexed list. You can also say rest of x, that will give you 2 and 3, right? You can also call operations on x, so you can map over it. So you can say map, and I can say increment x, yeah? So it gives me 2, 3, and 4. So what it does is increment is a function that increments everything by 1. And that then gives you a new list, right? So again, as you can see, I'm calling things on x, but if I go back to x is still 1, 2, and 3, right? So I defined x, that was the var, but it's not being mutated in any way. Every time I do an operation on the list, I get a new copy, right? Now, you might be thinking that that could be quite costly, but Clojure internally has a very optimized way of keeping these data structures. And it's actually very, very efficient, both in terms of memory and operations, right? So the message is you don't have to worry about the copies, but you get full immutability by default, right? So you can, for example, do filter as well. So if I say filter on x, so I can, well, say give me only the odd from X, and it gives me that, right? I can do a reduce as well using accumulators. So reduce will take in a function, let's say plus, yeah, on X, and it gives me 6. So what it does is reduce takes an accumulator, so starts by the identity, which is 0, and then of X is 0, and then it will start accumulating by applying the identity to the first element, then the result to the next element, and then that result to the next element, and so on. That's what effectively a reduce does.
So, Mash, so in this case, the first thing is that plus is effectively a function.
Plus is a function, exactly.
Okay, and second, if you want to reduce by your own function, how will you do that in Clojure?
If you want to, sorry, if you want to reduce over your own function.
Yeah.
Yes, so you would have an accumulator, right? So so if you reduce on something, effectively, it needs to be, I think it's called referential transparency or something of course, but basically the argument going in has to be of the same type as the result, right? And it has to have an accumulator and the next thing to apply to it, right? So if you think of plus, right? Plus takes in 2 or many integers, right? Or numbers. And then what does it return back is a number. Yeah. So it's the same thing. So the first argument needs to be able to be the result of the previous application of that same function. Does that make sense?
Yep. Yeah, it does.
And this is part of functional design as well. And I think if you go into category theory and all those kind of things, there is a name for this kind of function. And when you have functions like this, you have very, very composable functions. So in Clojure and in any functional language, you are encouraged to write composable functions. And this is one of those properties of the function that makes it more composable, right? But I won't go into that because that kind of takes you more deeper into the language of functional programming rather than the features of Clojure itself. So anyway, so moving forward, we have, so you can do pop and peek as well on the same thing. So if I say pop X takes the last, basically it takes away the first and gives you the rest back, and peek will give you the first thing, right? So you can use lists as a stack as well. You can also do a group by. So you can say, well, group by odd, right? X, and say it will group things for you. So it's returning here a map, and I'll show you what maps do later on. But effectively, it's got a key of true, the different results that were grouped by true, and the key of false and different results. So it takes the results of this function and groups each element by the result that it gave, right? Then the other things are cons and conjoin, which can be quite useful as well. So cons basically so if I do cons, let's say 0 to X, that will append to that list. And in this case, conjoin would also append. Conjoin is written like this, right? Conjoin would also append to the list, right? But actually, the two functions behave differently on vectors, and we can show you next, right? So before we move on from lists, are there any questions on lists?
Oh, anything?
No.
All right.
No?
Not at the chat.
No, from the chat, no.
Okay. Cool.
Yeah, we can move on.
All right, perfect. So before we move on, I just want to try again, just one more time to do this exception handling. So if I say, let's say divide 1 by 0, which is usually the example given, and say catch exception. Get message E. Yeah, that's what I was doing. Yeah. Okay, so it seems to be working this time, right? So what I've done is divided 1 by 0, and of course that's not allowed. That raises an exception, because if you see, if I do divide 1 by 0, I get an error, an exception, right? And I was able to catch that exception and just print the message, which was this divide by 0. Yeah. So moving to vectors. Right, so vectors in Clojure are also similar to lists, except they are an associative data structure, and the association is their index, right? So like map is also associative data structure. If you know Java, you know them by kind of hash maps, right? So you got key value pairs, yeah. That's an associative data structure. A vector is similar, except the key is this index, and it's kind of 0 index. So if I say def x, and this is, you define a vector using the square brackets. So I can say x is 1, 2, and 3, right? You don't have to escape that like you would a list, because Clojure only tries to interpret lists as programs, not vectors. Yeah. So now if I say x is a vector. Yeah. Now I can do the same things, the first, the last, it will work in a similar way. So I can say first of x, 1, and last, and so on. You get the point. The thing where it changes is actually in cons and cons. So remember we had the cons, and we said, well, 0, x. That would append it, right? Const does the append or insert at the beginning. But what if I do a conjoin, which also in list's case kind of inserted it into the beginning, but in this case it will append it to the end. Sorry, my bad. Conjoin. To 0. So as you can see, it's actually appended it this time, because the list is a optimized data structure to append at the beginning. Yeah. The vector is an associative data structure, and it's optimized for random access or random insertions. Yeah. So you have to be quite careful when using. So if you need a data structure where you need to kind of insert or append at the end and so on, don't use the list, because it won't be as well performing as a vector will be, right? And also you'll find it quite difficult to actually append to a list, whereas you can do it quite easily with vectors. Yeah. So otherwise, vector behaves exactly like a list. So first, last, as I said earlier. So you can call the same functions you would call on the other data structures, and you will get the same thing. Okay. Before I move on to sets, any questions?
So effectively, you can do whatever or exactly the same things that you can do with lists. So I mean, you can also do reduces, you can do inc, all of it, right?
Yeah, pretty much.
Would there be any other difference that we might need to consider?
I think with I think there are differences when it comes to destructuring, but I think this is the main difference. It's a data structure that behaves in a very similar way to a list, but it's optimized for you to kind of randomly add and remove things in different places within.
Right.
And it's an associative structure. Yeah. I think that's the main thing. You could probably call contains on it. I've never done it actually. If I say contains 3, I think x3. Yeah. So what if I do 2? Yeah. So you can call contains on it, and contains works quite. It's quite weird because if I look at x is 1, 2, and 3, and you saw that when I called contains 3, it said false, but there is a 3 in there. Actually, what it's looking for is, does it have, what the contain is asking is, does it have an element at position 3, which of course it doesn't. It has elements at 0, 1, and 2, right? So, but you can't call contains on a list. So if I say contains, because a list is not associative. So if I say x list contains 1, 2, 3, 3, yeah. So contains is not supported on a persistence list. Yeah.
I have a question too. The list can contain or can have elements of the same type, or can have several types of numbers, strings, and the same for the vector?
It can have elements of any type really. So that's one thing with Clojure. Of course, it's dynamically typed. So that doesn't mean that it's not typed, but they are heterogeneous data structures. Just like in Java, for example, you got your lists and arrays and so on. They are heterogeneous in the way that everything is an object, but underneath it, they may have their own concrete types. Only arrays won't. In Clojure, you can create a list of 1, and then 2, 3, and that's fine. Yeah. So usually, of course, you won't do that kind of thing unless this to me is a tuple, right? So tuple are a number of values that belong together but are not necessarily of the same type, whereas a collection usually is something of the same type. So Clojure will allow you to do it, but if you're defining something like that, what you're trying to do is create a tuple and not a collection. Make sense?
Yes. Yes. Thank you.
So moving on to sets. So sets are also associative data structure. But in sets, the key is also the value, right? So if I say now def, and sets can be defined with a hash or with a set thing. So I say def x hash 1, 2, 3. Yeah. Now if I look at x, it's a set, right? As you can see, I put 1, 2, and 3, and it said 1, 3, and 2, right? As you probably would know from your school set theory, that sets are unordered lists. So order is not guaranteed. It will appear in whichever order, so you can't rely on that. What is guaranteed is uniqueness. Yeah. So I can add to a set. So for example, I think cons would work to a set. Cons. So let's say add 1 to x. Oh, but it gives me a list back, won't give me a set back. I have to turn it into a set in order to. So let's say if I define this original set by 1, 2, 3, and 3, right? It's a duplicate key, won't let me do it, right? And even if I created a set where I had duplicate keys, it will remove them. I think, what does associate do? No, that's a map, right? Okay, so effectively, it has a set has the uniqueness, and it's by the way, if I think I could do into set maybe, yeah. So contains, sorry, as I did earlier with cons 1 to x, gave me a list, but I could actually probably do into set. Yeah. So as you can see, into basically takes the collection as a list, because cons returns a list back. Although it takes a set in, it adds one to the set and gives you a list back, right? So that's why it can have duplicates. What I'm saying is, take that list and stick it into a set for me. And as soon as I stick it into the set, it will deduplicate that list again. Make sense? And then if I do contains on this set, I say, well, contains, oh. And then I say, well, x3, like I did before, this time is true, because actually, as I said, the value is also the key, and it is an associative data structure, so contains works on that. Yeah. And that's sets. Any questions before we move on?
No.
No? All right. So let's move into maps. So by the way, the reason I'm taking you through these native data structures is in Clojure, you don't really create kind of, in an object-oriented language, you've got value objects and all these kind of things. In Clojure, you are dealing with data structures most of the time. It's a list processing language. Its power is within handling data, right? And if you think about a lot of the apps that we currently write, like web apps and so on, what are they other than kind of data transformations, right? And maybe some persistence. So we take data from like JSON, we transform it into something, we do some operations on it, we persist it into a different format. It's all, and we bring it back and we present it in JSON or HTML and so on. In the end, they're all data transformations. And that's what makes Clojure such a joy to work with when dealing with applications like that, right? And that's why I am kind of spending a lot of time on the native data structures, because they are the kind of, they underpin the language in a way. So maps. So let's do a map. So map is defined like this with a key. So I can say X is X. Oh, I don't know, 1 maybe is better. And Y is 2, yeah. And Z is 3. So that's a map. So it's keys associated with values, right? Now you saw me doing this notation of colon, and the colon effectively is a keyword in Clojure, and colons are there for, so the keywords are there, they evaluate through themselves, right? So they are a very efficient way of they make really good keys in maps because they evaluate to themselves. So you'll never find out that you need an enumeration or that kind of thing, because you have this concept of a keyword, and you can define a set of keys, and that's an enumeration, right? So keywords rather, and that's it. So they always evaluate to themselves. That's why they make good keys, right? So then in maps, you can actually say, well, what's the value of X? And you can actually use the key as the function call on the map, yeah? And it'll give you 1 back. Or you can do it the other way. You can make X the function call and give it the key, and you'll still be the same, right? It has all the other things. You can say first of X, it gives you the key value pair of the first key value pair, and so on. So you can do all the things that you would do You can do map, reduce, conjoins, everything on there. You can also do contains, but this time contains is on the keys as it always have been in associative data structures, and the keys are X. So if I say, sorry, contains X is true, but if I say W is false, yeah? And maps you will use a lot in terms of representing data structures into your language. And you can say, well, in Java, it's kind of, you know, they say use the types and so on. In Clojure, we don't have that. You have Clojure spec and so on that will allow you to do runtime checking on the kind of structures that a function should receive. And it gets you somewhere there, but at runtime. But, you know, Clojure is dynamic language. So people used to more statically typed languages will find that a bit weird. But if you know Python or, you know, any other dynamic language, then it won't be it won't come as a surprise to you, right? So before we move on from maps, any questions?
I have a question. Can we use strings as keys for maps?
Yes, you can. Yeah. They you know, a string in the JVM kind of evaluates to itself as well, right? So yes, you can. So if I had that Y, I could say, rather than that, I could say X is 1 and Y is 2. Yeah. Now, the problem with that is, could you think I could do that? No, because you can't, a string cannot be a function call, whereas I could do it with a keyword, right? What I can do is the other way around. So yes, you can. It's not idiomatic, and I have a feeling it's not as efficient as keywords are.
Okay, thank you.
Yeah. Okay, so moving forward, we have records. So records are the closest thing you'll get to a Java value object. So if I say def record, yeah, and then I can say the name of the record, and then the fields, right? So I can say def record person, and I can say person has name and age. Yeah. Okay. So now what this allows me to do is to create value objects called person, right? So I can say def Y is a person. See, it uses the same kind of new person thing. And I can say the name was Mash. Yeah. Now, if I look at Y, it's a person record with name and age. Yeah. And I can use it as if it was a map as well. So I can say, what's the name of Y? Yeah. The only thing I can't do is create a add or remove. So it enforces that this person can only have name and age. I can't add, for example. Let's see if I associate, yeah, and then like I would put in a map. So associate map key values. So into Y, let's say I wanted to add, I don't know, address. Yeah, and give it some address. So, oh, it actually allows you to associate, but it doesn't allow you to construct. That's surprising. I never actually tried to do that. But yeah, so, but I can't really create a person with in the beginning with the address, but it works in the same way. And can I then do, let's see. Yeah, I'm experimenting so can I do that? on this list. Okay, so it seems that a record is pretty much a map, really, except when at construction time you have like this kind of new constructor, right? Where you don't have to provide the keys; it has these built-in keys, yeah, which you define as part of the def record. Yeah. Any questions?
Yeah, now, for example, now that you have created this person, Mash, can you change his name, or would it violate the principles of functional programming? Of
no, you can, but it won't let you, right? Because as I said, as you saw earlier, if I still do, I define Y, yeah. Y is still the same. You can't actually change it.
all right.
So what you got back is a person that has name, age, and address with the associate assoc function, but that's a new person. That's not the same person that I. So there's no changing anything. This is what I mean, that like this can become quite jarring, that like all these operations I'm doing on these data structures, and you think, oh, I'm changing that particular thing. No, I'm not. I'm actually creating a copy with the new thing. The old thing remains as it was. So the data structures are by default immutable.
All right.
Yeah. Make sense? Okay, so let's move to destructuring. So that's kind of the 101 of the native data structures. Okay, so I need to move a bit quicker if I was to take you through a bit of a whistle-stop tour. The destructuring works in quite a nice way. Is that actually you can say so earlier, remember I had this infix thing, yeah, and I was doing first and so on. So macro, def macro. X, yeah, and I was doing first and second and third. Actually, I can just destruct in here, and I can say first, second, third, or last, as I was doing, or I can even give them better names. I can say the first is a operator, operand, op1, operator, and op2, yeah. And then I can now say, create me a list, or I can even do that. And then I can say, start with operator, and then give me the first operand and the second operand. Yeah. Oops. I always forget that. Infix, yeah. And I've created the same macro, but in a much more succinct way. Yeah. And I'm actually using destructuring here. And I can now say infix 1 plus 2. Oops. I couldn't find operand in this context.
Maybe it expects a vector as a, no?
No, I think, let's see if I do a list. Yeah, sorry, it was just the deref that was the problem. Yeah, so I'm creating the list with the destructuring, and that works, right? So basically, all it does is it takes in the collection and it's destructuring this collection. I mean, you can like let is a way of defining kind of vars within a scope. So I can say let x, y, z to be 1, 2, 3. Yeah. I can say print ln x or just return x. Yeah. So that should be z. So now what that does should do is to give me 1 back. Yeah. Yeah. So I can even, if I just want x, obviously, because I don't care about the others, I can do that and give me. Yeah. So you can reach into collections and destructure. So if you use the other kind of languages that allow that, then it won't be a big shock, and you can use that in, as I showed you, in functions, but also you can use it as tuples. So for example, if I say defn is a way of defining functions, so I can say hello, right? And this function takes nothing as a parameter and would return a return two things. So it may return my name and it may return my age. Yeah. So there are two things, and that's what I meant by a tuple. This function returns two. So if I say hello, it will return this. Now in like, you know, you then pull it out and then you have to do first is match and so on, but you can actually quite easily say let, so then you say, well, name, age, oops. And then I can call hello, right? And then I'll say, well, now print, I can even say return string name is age. Yeah. Okay. See? So that's also a very kind of concise way of handling with tuples and multi-value return. Yeah. Which can be quite difficult in other languages again, but unless you then have to start dealing with value objects and those kind of things. Okay, so, and you can do the same with maps as well. So for example, if I said let in fact with maps, you kind of do it like this. So you say keys and I can say name, and this is a map, right? And then I can add, so name is match, age is 43. And now I can say, give me name back, yeah? Yeah, so this, as you can see, you can reach out and you can name the thing, in this case, according to the key, and it will know to kind of create a keyword and find that thing and assign that value to this var. Yeah, and then you can refer it to it as that var. So again, this is another good reason to keep your keys as keywords rather than strings, because you can do all this weird and wonderful destructuring, which can make code much more readable and succinct. Yeah. Any questions before we move out of destructuring?
Would it be possible to do something like the last expression, but by reusing the hello function?
You can do, yeah, you could do something, but the hello function will then need to change to return a map, right?
All right.
Like this. And now it's returning a map and you can destructure it accordingly. Yeah. Yeah.
All right.
Make sense?
Yep.
Excellent. All right. So next thing is list comprehension. So how do you deal with lists, right? So in Clojure, everything is an expression, but Clojure is, again, pragmatic, and it knows that sometimes your functions are side effect ones, but for example, is not one of them, right? So if I look at x, what was x? Let's define x again. So in this case, x is 1, 2, 3. Yeah. I can now do for x. So for, let's call it, I don't know, my element to be x. Yeah. and then I can, let's say, I don't know, say plus 1x. Yeah, so this is the same as my, oh, sorry, 1EL. Same as what that map did, right? That map increment increment x gives you the same result, right? So sorry, let me just call it increment. Yeah. Yeah, so it does the same, right? So, but that's a for loop. It does exactly what a map is doing in this case, but it gives you more control. You can iterate over, and everything you return, every return of your each iteration effectively is a element in the collection that will be returned back, which is usually a list. Yeah. So you can then do an into it and turn it into any other data structure you want, but it will return a list back. Yeah. You can also do kind of let and whens in things. So you can say let. So in this case, I can say let now I don't know, Z is an incrementation of EL. So I can already start using EL here. And now I can just say, well, just return EZ. Yeah. Same thing. Yeah. So you have a for let, but then you can use a when. So it's called like a flower statement. So you can then inside and say when, and you can say the result is odd. So EZ is odd. And you can do a filter in there. Yeah. So again, as you can imagine, this could be quite powerful, but written in a quite a succinct way. So it's kind of iterating, performing in something, and filtering or doing something, filtering it out at the same time. Yeah. So that's kind of the let. You can also do while, which is similar thing, but I'm running out of time, so I'll move a bit quicker. Do sequence is for is same as for, but it actually allows you to, so do sequence allows you to have side effects. So it returns null basically, but allows you to, so I can say EL X println EL. So 1, 2, 3, but returns a nil, right? So it's not expecting anything back. If I did that as a for, it would return a collection called nil, 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 nil. Yeah. So that's it. So when you do a user do sequence, it's for side effects. So like when you're iterating and then causing side effects, use these sequence because that's automatic in Clojure. Then you're kind of telling the reader that this is something that's causing a side effect. Yeah. Next thing is lazy eval, but I'm gonna skip that because it's not as impressive and we don't have a hell of a lot of time. But mutating state is quite interesting. So up until now, as you saw, you can't mutate state, but Clojure has these 4 different ways of mutating, of variables. So vars are, as I've been mentioning here, they are kind of thread local global variables effectively. Yeah, so you define them with def. Yeah, defx is a var, as I was defining them earlier, but they're thread local, usually not change. You can, of course, overwrite them, but you can't modify them. And usually they just, you normally have them as something that only is defined once and then used, but never changed. So that's when you would use vars. Atoms are uncoordinated synchronous access in the sense that they allow you to have to change state between threads and everything else. What it will do is it does a read replace. So if another thread goes in the middle, it will back out. Yes, so it does provide the thread safety and it's available to all the different threads. So for example, if I say def x atom 100, yeah, then I can, so now if I'll have to dereference X, right? And give me 100 back. But if I want to change X, I can say swap, and that will take an atom and a function, yeah? So swap X and function is increment. And now if I refer to X, wow, like now I've changed state, right? So this is the only way that you will be mutating state. So I've mutated X in its place, but I've used swap. So what swap does is it goes in, it's synchronous, so it will wait. It will make a thread safe operation of increment, and it will get back. So when you have counters and things that only one value needs to change, then you use atoms, yeah? By the way, that bang is a Clojure convention. So something that causes a side effect, you have this exclamation mark in the end, in the name of the function, yeah? So basically, and then you have, the other one I will show you is ref. So for example, ref is transactional memory, right? So you can say def account 1 is ref 100, yeah? Yeah. And def account 2 is, let's say, ref 0, yeah? Okay. Now I can deref that, and I can say, well, what's account 1? And it'll tell me it's 100, and what's account 2? And it says 0, right? Now, what I want to, let's say, do a transfer, a balance transfer, yeah? And then I can do a do sequence. And this is the kind of the, so I can say alter, and in this case, the ref itself, which will be account 1. So move money from account 1. Yeah, so let's say minus 50. Move 50 pounds from account euros, and then add them to account 2. Yeah. So alter is a special statement like swap was for atoms. And this do sync. I think it was do sync. Oh, sorry,
you had a typo.
Yeah. So now if I go back to account 1 is 50, and account 2 is also 50 because I moved 50 euros, right? But let's say if I was to say something happened in the middle, right? I was silly, and let's just print after doing a minus from account. So now we have 50 and 50 in both accounts, right? So if I run it again, it should, account 1 should have 0 and account 2 should have 100. So I'll even print here account 1 and the value of account 1. But then what I'm gonna do is divide by 0 here, so that I get an exception in the middle before I could do the other one. Yeah. Okay. So as you can see, account 1 is 0 inside the function when I called it. Yeah. So it said account 1 was 0. But actually, when I see, but then an exception happened, it's still 50. So what it's done is it's rolled back my change. Yeah. So this is STM, software transactional memory in Clojure. You can, if multiple things need to change, so it's thread safe and it will change things. So you don't have to do all this sync awaits and all sorts of things that you may have to do in Java.
Mash, if we were to use, I know this is probably a bit more advanced, but if we were to use transactions, let's say a database transaction, would it be useful to use this do sync approach instead of using a regular transaction?
No. This is memory transaction. So this is transactional approach to changing, mutating state. It's not about database transactions. Works in a similar way, But in database transactions, if you do have transactions, then you would use a framework the framework's way of hooking into the JDBC transactions, and you start. So they are different. Yeah.
All right. Okay.
Mm-hmm. Right, so moving forward, I could show you a bit of Clojure and partials, but we don't have a lot of time. I'm gonna show you how Clojure testing works. So, by the way, before we go there, any questions?
Don't be shy. No?
All right.
Right.
Okay, so let's move into like testing. So for example, this is a how you write testing in Clojure. This is Clojure test. There is also another framework called Midge. So here's a function called leap year. Takes a year and says, well, for now it just does a very rudimentary kind of divide by 4. Of course, that's not all the rules. So here, for example, if I, let's say, actually add a leap year, and I'm saying call a leap year with 1996 and say, and this is equal to false. This is actually a Clojure test thing, right? But equals is just a equal operator, right? You can do anything there. So if I run this, you can see that it's it says, so it gives you that kind of same thing, you know. It says, well, you're saying leap year 96 equals to false, but actually true is not false, right? So it's giving you it's telling you what's wrong. So that's how you kind of, so you write the test. If you want to do mocking, so if say, let's say leap year was calling that 0 and you wanted to mock that 0 function, yeah, that you would do with redef. So there is a thing called with redef. And then you can rebind the 0 function and then call the test within it, and it will call your 0 function rather than the one available outside that scope, right? So that's how you would mock, but mocking is, you know, like that basically means that your functions are have state or very complicated and so on, and Clojure tries to deter you away from that. And in fact, that's why they purposefully not actually, with redef is not a testing thing, but they purposely not added any kind of better mocking ability in Clojure test, but you can do it if you want. So that's Clojure test. I mean, of course, it runs very quick if your REPL is running, and you know it's built into the language. There is another way of testing, and I'll quickly show you that, and that's Midge. Let me just show you in Memento. So for example, here, I can show you Midge-based tests, which are actually, let's say, these ones are mocking, and you're using what's known as a meta constant, right? So here is saying call delete activity, provided that delete activity has these 2 calls inside it. Activity has entries. If activity has entry is called with the same thing, that's all that means, then return false. And when the delete activity is called, make sure it's called once and return 1 when it's called. And then here I can say, well, when I call it, expect 1. So it's doing a verify that this is called once, that it will return 1, and that I expect that 1 back. And it also mocks has entries to return false. So this is saying delete an activity with no associated data time entries. So I'm saying is when an activity has entry is called, return false, that fulfills the no associated time entries. And when delete activity is called, make sure that when there are no associated ones, delete activity is called only once. Yeah. So this is Midge. It's written by Brian Merrick, and that's another testing framework in Clojure, and it provides a much better support, as you can see, for mocking. Yeah. You can also, for example, even in Clojure test, you can do this throws clause where it says, if I call this and the delete activity has entries, I've tried to delete it. It says it's a bad operation because you can't delete things that are so it's expecting this exception. Yeah. So that's another way of testing. So there is one more way of testing, and this is generative testing, right? So here is a spec. So for example, here I have a Mars rover kind of rudimentary way, and I'm going to take you very quickly through Clojure spec as well. If you're confused, please forgive me because I don't have a lot of time. And Clojure specs deserves a lot more time to explain. But so for example, I have this function called move. It takes in a rover and commands and just returns the same thing back, right? So what I'm saying is in Clojure defs, I'm saying that there is a thing called commands, and it's a string that matches basically FFF effectively. So commands are just forward only at the moment, right? And then, so it's kind of almost like a type. It's saying it's a type string, but actually it can only have values F repeated, yeah? And there is another type called X, or thing called X, spec called X, and that's an integer. Another one, Y, that's also an integer. A D, which is direction, that's a keyword, right? Now then what I'm saying is that a rover is basically a set of a data structure that has X, which is an integer, Y, that's an integer, and D, that's the commands, and that's the rover. And my function move has arguments. That first argument called rover matches the spec rover or type rover. The second argument called command matches the spec commands. Yeah, the return argument must be of a type rover, which is it must have X, Y, and D direction. Yeah. So then I can, I mean, there's a bunch of normal tests that are written, but I can also do a generative test on there. So what I'm saying is, do a generative test on this, call it my test on move, right? I'm instrumenting it here, but do a generative test. When you do generate, when you look for rover, create a hash map. In this case, I'm saying, well, X is any positive integer, Y is any positive integer, D is an element of north or south. So it will randomly pull values out of here and call my rover function and always see if the return value is correct. It defines to my specification of what a rover is, which is X, Y, and a D, right? And also says every time you need commands, these are some of the commands that you can send, right? So it will just rotate through them. So I'm providing some value generators. And then if I run this, yeah, so there are no errors. But let's introduce an error, like kind of a bug. So here I say when the row value is bigger than 19, so just a randomly chosen value, return an invalid thing. Yeah, so this is kind of a dummy bug that I've introduced in my code. And if I do this, see, it catches it out immediately. And if you look here, it's saying, sorry, as you can see, so it's saying that this thing, I'm pointing here, yeah, as you can see, it's saying that it's failed because you said that a rover must contain Y and D, and it doesn't contain it, right? And that was the bug that I introduced here. So in this case, X is there, but there's no Y and D, which usually is provided in the normal cases. So if I remove that bug again and do my generative testing, it works. So it's actually property-based testing as well. That's kind of very useful. So you can have this combination of property-based tests here and normal example-based tests here. So that's another way of testing in Clojure. You can do it in other languages as well, but not as nicely, in my opinion. Right. So I've shown you Clojure spec a little with kind of a whistle-stop tour testing and so on. There's a lot of things. There's a real project, there's Clojure script, and there's JSON, and there's a lot of other things to show, but we've kind of run out of time, unfortunately. So I'll stop here. And if you have any questions, you can ask questions.
Thanks, Mash. Any questions, guys? Okay, Jose Miguel, he says, I'd like to know your opinion about using other Lisps, like Racket, Common Lisp, for example, to avoid JVM startup times. And do you have suggestions for maintaining large code bases on Lisp?
So I personally haven't used other kind of Lisps. If you, I know there are other kind of Lisps available. I haven't used them myself. I think the ecosystem is not as good or as big. Clojure has a much more, it's much easier to learn, I think, because it's on the JVM platform, and it's much easier to deploy because in the end it is a JVM application, right? So using other list types, I think you can, but you will not be able to benefit from a much richer ecosystem. They are more archaic languages. I'm sure other people may disagree, but that's my view. The second question was managing a large code base. You know, that's a problem with a lot of dynamic languages, and that's where Clojure spec and pragmatic schema come into play as well. You can do runtime checking, but also you should kind of move more towards a services-based approach where you're not allowing your code base to get too large. But I think this is an advice for anything really, right? For any language. But I think with dynamic languages, it's more pertinent that you don't allow your code bases to get too large. You split in cohesive, decoupled modules, like kind of, I hate to say microservices, but I won't keep them micro, but cohesive services, cohesive components. And that's the way to manage any code base, and especially one that is kind of dynamically based. And again, testing well-placed tests, not complicated, not too much mocking, but mocking where it's really needed.
All right, there's another one. Sorry, one more, which is how you consider the popularity of the language is growing.
It's an interesting question, actually. Clojure grew 4 or 5 years ago. It was growing quite well. Clojure script was growing as well. Is one thing I couldn't show. Clojure and Clojure scripts are very much the same language, but Clojure script compiles or transpiles into JavaScript, and it's actually a really good language, and it has really good tool sets. But the adoption has tailed off. It's still being adopted, but not as fast as it was. But it's still on the up. It's a language that has some real vocal fans. You might know Bob Martin. Uncle Bob is one of them. I think his latest post was on Clojure. I haven't seen it yet. At one point, he called it the last language or something because he got a bit too excited, in my opinion, about it. But yeah, it has a great community. It's actually a very viable language. 2 or 3 of our internal projects with our clients are using Clojure. We write our internal applications with Clojure as well. So, I mean, for me, it's the language of my choice, really. I think it allows me to write simpler code, a lot less accidental complexity, and get things done quicker and keep them very maintainable. So for me, it's my language of choice, but of course, that is just a personal opinion.
All right, the last one says, do you use Datomic?
I have used it. I like it a lot. It has a bit of kind of a weird, it's a bit expensive, but I think if you have the need, it's really good, because the Datomic takes this immutability concept of Clojure data structures into a database. And works really well. I know you can even, you can spin it up as a managed service in AWS quite easily. I like it as a technology. I love it, and because it does immutable data structures, it maintains a record of everything that you've done. So you get a system of record for free. So things like, if you have anything that requires a system of record, that basically means that every single operation that you have done on your database, you can get back to, and you can get back to any state of your database at any time, any state of your table or collection and so on. And this is amazing, right? But I'll be honest, I normally use my applications with a relational database or something like DynamoDB or something like that. You know, it's enough for my needs, but I do like the technology.
All right, that was the last one. Well, thanks, Mash. Thanks for this amazing session. Thanks everyone for joining us. And well, join our meetup group, the Codurance meetup in meetup.com, and we'll be posting new events during this convoluted times. All right.
Thank you.
Thanks,
Javier,
everyone.
and thank you, everyone.
Thanks, everyone. Thanks, Mash.
Mash.
Thank you, Mash.
Bye-bye. Bye.